All right, intro-rotational kinematics problems. There are 7 of these. And let's start with a record player that starts out spinning at 6 2/3 radians per second and slowing down at 1 1/9 radians per second squared over a certain amount of time. So initially spinning at, this will be the original speed, this will be the acceleration, and this will be the time. So what we can do is make our Vofa list, but now with the angular variables, and pull from the story the numbers that we are given. So we are given the original speed, the acceleration, and the final speed. And then we are asked for the final angular speed and the angle that they turn through, so those guys get question marks. So we're asked for the final angular speed first, so we need the no theta equation, which mirrors the no s equation. And we just need to use the angular form of this equation. Now it says it slows down, so we need to go back here and make sure that that is a negative 1.11. And using our calculator, we get a speed at the end of those 3 seconds as 3 1/3 radians per second. Now we can choose almost any equation that we want to solve for theta. So we can use this one, as I will here, or you can use anything else that has a theta in it. You just need to make sure that you grab the right numbers from your list of givens. And make sure you square before you multiply. And we end up with 15.0 radians. Notice that our units here, we need to have radians per second and radians per second squared and seconds. All of our units need to agree with each other. Which brings us to number 2, where we're told it turns through half a revolution. That is an angular measure that is not in radians. So as we come over here to make our list of givens, we're asked to calculate the angular acceleration, and you're told the units that you need to have. And it starts out from rest, so that'll be a 0. Goes through a time of 3 seconds again, and this time it's half a revolution. So the first thing we're going to need to do is convert from half a revolution into radians. So 1 full revolution is 2 pi radians. So a half a revolution is pi radians. That would be acceptable in math class, but in physics you need to have 3 significant figures. So that will be 3.14 radians. Now we can use any equation that doesn't have an omega f in it to solve for the angular acceleration. So we can use the same equation that I used in part B above. First term will go to 0 because the angular speed starting out is 0. And then we have 3.14 radians, 1/2 of the angular acceleration that we're looking for, 3 squared. Couple of steps of algebra to rearrange for alpha, and you get 0.698 radians per second squared. Calculating the final angular speed, you can use any equation that you like as long as it has omega f in it. So let's use this one. Again, the first term is going to go to 0, but now we're going to use our answer from part A to get this answer, which is 2.09 radians per second. All right, for number 3, now we have an initial speed that is not 0. It starts out turning at 1 speed and then ends up turning at another speed. Because spinning donuts with his car means that the wheels are slipping on the pavement. So once again, if you take a look at the question, that tells you what you don't know. Angular acceleration we don't know, and angular distance we don't know. And now we take a look at the story to figure out where each of these numbers go. Initially turning at, that tells us our original angular speed, and then reaches is an indication of some time later, 4.71 radians per second, and then after a time of 1.5 seconds. So to get the angular acceleration, we're going to want to use an equation that does not involve theta. And we can rearrange to solve for angular acceleration before we plug in numbers, or you could plug in numbers first since you're given numbers in this problem. Make sure you subtract before you divide. And we get 2.76 radians per second squared. Once again, a numerical answer requires units. All right, the angular distance covered by the car as he is spinning his car around. So the wheels are spinning and the car is rotating around. And we can use any equation that involves a theta. Since we have the other four, at this point we have the other four kinematic quantities. And depending on the equation that you choose, you may or may not have algebra to do. And that gets us an angular distance that he turns through in that time of almost 4 radians. So about 2/3 of a spin around the circle. All right, now we're going to tie in linear distance and take a look at how linear distance relates to the angular distance. Before we can calculate any of our angular quantities, we need to convert the linear quantities to the angular quantities. So we have our circle here with a radius of 0.25 meters. And so the teenager's car is initially spinning with a speed of 20 meters per second, but that's for a radius of 0.25 meters. So the linear speed of 20 meters per second is going to get converted to the angular speed, 20 over 0.25, gets us spinning at 80 radians per second. And then speeds up to 60 meters per second, but the radius stays the same, which gets us a rotational rate of 240 radians per second. Which allows us to find the initial and the final angular speeds of those two wheels. Now that we have them, we can do the usual kinematic list to find the angular acceleration and the angular distance, and then we can convert back into linear distance to figure out how far a point on the rim of that wheel has traveled in that amount of time. Keep in mind, that's not the linear distance that the car travels, that's the linear distance that the point on the rim here. So we have a point on this rim and it's going around and around and around while the car is traveling forwards. If there was a piece of string stuck there and it rolled and rolled and rolled, how long would that string be? Okay, now that we have our speeds converted and 1.5 seconds for the time, we can get the angular acceleration with our favorite kinematic equation. And again, you can either rearrange the equation first or you can plug in the numbers first. And you can get 107 radians per second squared. And then we do the same thing for the angular distance covered. Starts out at 80, and we can use the angular acceleration once you find it to get 240 radians. Now the linear distance covered by a point on the rim, this is s equals r theta. If you remember, c equals 2 pi r. The total circumference is the total going around times the radius. And all we've done is convert the total circumference to a partial arc length. And then that corresponds to, instead of having a total distance going around, we have a partial distance theta going around. Or sometimes it's more than once around, as in this case. So the radius is 1/4 of a meter. And we have 240 radians that we got in the previous section, which gets us that string would unwind for a distance of 60 meters. All right, some more angular kinematic problems. We have a bike wheel that's 70 centimeters in diameter. Now, if the diameter is 70 centimeters, that means the radius is 35 centimeters. And then we're given several angular quantities. So we have a time of half a second. It turns through 1.57 radians, also known as pi over 2. It starts at rest, so that's a 0. And then A and B ask for the angular acceleration and the final angular speed. So, using our kinematic equations of motion that are adjusted to be angular, we can use this one to find the acceleration, where this whole term goes to 0 because it starts from rest. And 1.57 radians equals 1/2 alpha of half a second squared, multiplying both sides by 2 and then 2 squared. So 8 gets us an angular acceleration of 12.6 radians per second squared. For part B, we can now use the angular acceleration that we found in part A to get the final angular speed. Again, since the original was 0, that term goes to 0, and we have, that should be 12.6. 12.6 times, again, half a second, gets us 6.3 radians per second for our final angular speed. Now, suppose we have a tennis ball. So we have a wheel here, and that's 35 centimeters. So we have a tennis ball wedged 15 centimeters from the axle while it's going around, and this should be pi over 2. So from there to there, what is that arc length? Well, the relationship is s equals r theta. Part of the circumference is part of the angular measure around the circle. So 15 centimeters times 1.57 radians gets us 24 centimeters for that arc length. All right. Now, what if the angular acceleration is not constant? What if it changes in time? Well, now we need some calculus to get the relationship between alpha and omega and theta. The kinematic quantities, the kinematic equations, won't work as soon as alpha is not constant. So we're going to have to derive an expression for the angular speed as a function of time using the relationship alpha equals d omega dt. which we then rearrange so that the omega, which we're looking for, is on one side of the equation and everything else is on the other side, so that when we find the antiderivative from the original to the final, we're going from time is equal to 0 to time is equal to t later on. All right, now we will substitute that. I'll write it down a little bit lower here. 3t squared minus 2t, that's alpha. And we're going to integrate from time is t equal to 0 for some time later on, where omega f is the function of time. So the left side of our antiderivative here will be omega, and we'll go from the original speed to our final speed, which we could write as omega as a function of time. And then the other side, we will find the antiderivative of this expression, where we increase the exponent by 1 and then divide by the new exponent. So we have 3t, and now this is cubed, and we divide by the new exponent. And then the 2 goes along for the ride, and then we increase the exponent and divide by the new exponent. And then we evaluate it at our limits between 0 and t. Now I've chosen the coefficients so that they disappear. And the left side becomes top minus bottom when we substitute them in for a variable. And then the right side of the equation becomes t cubed minus t squared. And then when we plug in the lower limit, 0, for both of these guys, that is 0. So we don't need to write that. Now, there's no information given here about what the original speed is, so we should leave our equation like this, where here's our speed as a function of time, and whatever the original speed is goes here. Probably that will become 0 at some point later on. Oh, if you look down here at part D, if the flywheel starts at rest. So later on, I'll tell you that guy starts at 0. But for right now, we need to leave it as omega naught. All right, now, if we're going to look for the angle through which this flywheel turns, we need to use the relationship between the angle and the angular speed. Now, if we're going to derive the expression, we need to start with the relationship between the angle and the angular speed, and then rearrange it, just like we did before, so that the angle is all by itself, d theta, and everything else is on the other side. And again, we will find the antiderivative between the original starting position and the position at some later time, at time is equal to 0, and then some later time. Now we have an expression for the angular speed that can then go in here to find the antiderivative of. And we will go through exactly the same process here that we did above, but using a slightly different equation. So our theta our d theta just becomes theta. And then when we substitute in on the right side, we have t cubed minus t squared plus omega naught, and then dt. And using the rules of antiderivatives applied to polynomials, we will find that this becomes t to the 4th over 4 minus t cubed over 3 plus omega naught t. And then we will need to evaluate it between 0 and t, just like we did before. The upper limit becomes all t's and whatever coefficients we have, and the lower limit turns out to be zeros. On this side, we will end up with theta t minus theta naught, just like we did with the omegas. And then we'll take the theta naught over to the other side. So we will have theta t equals t to the 4th over 4 minus t cubed over 3 plus omega naught t. And then this minus theta naught will become a plus theta naught on the other side. And there's our expression that we have derived as a function of time. All right, now, The maximum speed comes at the time when the first derivative of the speed is equal to 0. So max omega at, it's not accelerating right now. So what we need to do is we need to take the expression given at the beginning for angular acceleration, set it equal to 0, and solve for t, and then take that time and put it into the equation for omega to get that speed. So the angular acceleration expression is 3t squared minus 2t, and we set that equal to 0. So we can factor out a t and get 3t minus 2, and then set each factor equal to 0. So at t equal to 2, and at 3t minus 2, so that will be t is equal to 2/3. Those are the two times at which the angular acceleration is equal to 0. At one time, the angular speed will be equal to omega naught, and then at the other time, well, let's find out what that is. So omega at t is equal to 2/3 of a second, so that will be 2/3 cubed minus 2/3 squared plus omega naught. And we will assume that omega naught is 0 for this part of this problem. So the speed at that point will be 0.148 radians per second. And it doesn't matter if it's plus or minus. It will turn out to be minus. But the speed is going to be plus, because the speed is the absolute value of the velocity. So this tells us that it has stopped spinning forwards and it's now spinning backwards. All right, part D, calculate the next time at which it stops. So now we're going to take the expression for the angular speed and set the expression for the angular speed equal to 0. So we come back up here to part A, and we have t cubed minus t squared plus omega naught, and now I've finally remembered to put in there that it's starting at rest, so that guy is 0. And we can factor out a t squared, because that has a t squared, that is a t cubed. Set these two guys equal to 0, so t squared is equal to 0. T minus 1 is equal to 0, so t is equal to 1. So it starts at rest, and then 1 second later, it is back at rest again. Now, how far did it go in that time? So from 0 second to 1 second, how far did it go? And now we will take our expression back in part B. So t to the fourth over 4 minus t cubed over 3 plus, oh wait, that guy is 0. And then this guy is, well, how far did it go from where it started? So wherever it started, we don't really care. What we care is how far did it go away from this guy. So we can set this guy equal to 0 as well, because all we're doing is measuring how far away from that point. And now we're going to plug in 1 second. So theta at 1 second is going to be 1/4 minus 1/3. That's equal to 1/12 of a radian. In decimal form, 0.083 radians. All right, here's another problem where the acceleration is not going to be a constant. Well, how can you tell that? Well, one is the acceleration could have a t in it. Another one is, in this case, the angular speed is not linear. As soon as the angular speed is not linear, in this case it's parabolic, that means that the acceleration is not going to be constant. For part A, the times at which the ball is not rotating, the speed is 0. So we will set the speed equal to 0 and solve for t. We have a quadratic here, and we can start by factoring out a 2. And then we can factor this. and set each factor equal to 0. So 2t minus 1 equals 0, and t minus 1 equals 0. And that will get us 2 times, at half a second and at 1 second. Now to get an expression for the angular acceleration, we need to do what we did last time and use the relationship between angular speed and acceleration, which is take the derivative of angular speed. So we're going to take the derivative of this expression that was given at the top. In this, we're going to be running the antiderivative process that we looked at last time in reverse. So this time the exponent is going to come down and multiply by our current exponent, and then we're going to reduce the exponent by 1. So that 2 is going to come down, multiplied by 4, become 8. Then the exponent is going to become 1. And then there's a 1 exponent up here. It's going to come down, multiplied by the negative 6. And then the exponent will become 0. And anything to the 0 power is 1. So what we have here is the angular acceleration as a function of time is going to get us 8t minus 6. Now, the angular distance, again, we will be using the relationship between angular speed and angular distance, except we will multiply both sides by a dt and find the antiderivative of the angular speed. So we will substitute in for omega the expression that is given at the top, 2 minus 6t plus 4t squared dt, and we will evaluate between 0 and t. And the distance covered is just the change in the angular position, so we don't really care about where it started. All we care about is how far did it go. Finding the antiderivative of this, the exponents will increase by 1, divide by the new exponent. Exponent will increase by 1, divide by the new exponent. Exponent will increase by 1, divide by the new exponent. And cleaning this up a little bit, theta, how far is it going to go? 4/3 t cubed minus 3t squared plus 2t. All right, how far will the flywheel have, or the ball have spun through when it reaches the second stopping time? So 1 second is the second stopping time, and that angle at 1 second will be 4/3 1 cubed minus 3 1 squared plus 2 times 1. And that gets us 1/3 of a radian, which to 3 significant figures is 0.333 radians.